Hey everyone, in today's video we're going to be talking about electron configuration. So first I'm going to talk about ground state versus excited state for electrons. So electrons can occupy energy levels or shells that are around the nucleus, and they can jump between levels if they gain or lose energy. And they have to occupy a fixed energy level. They can't just be like in a space between them. So ground state is the lowest possible energy level, and it's closest to the nucleus and it's most stable. The excited state is when an electron absorbs energy, it jumps to a higher energy level that is farther away from the nucleus. And so it's a higher level, so it's an excited state. And this is temporary because the electrons return to ground state where they are more stable. And they release absorbed energy when they do this as a photon of light. So now we're going to talk about the Bohr model. So in the Bohr model, the electrons orbit the nucleus in fixed paths called orbits or energy levels. And each orbit has a specific energy. And electrons in the orbit have a fixed energy amount. Electrons can only move to a higher or lower orbit by absorbing or emitting a certain amount of energy. And electrons absorb energy, they jump from a lower orbit to a higher orbit. And then when they fall back, they release energy as light. So now we're going to talk about the quantum mechanical level. And this is a modern model of the atom which replaced Bohr. And electrons are in regions called orbitals, which they're most likely to be in. And there's also the Heisenberg uncertainty principle, which says that we don't know the electron's exact position and velocity at the same time. And we can only predict the probability of finding an electron in a certain place. So next we're going to talk about atomic orbitals. And atomic orbitals are regions that are around the nucleus where electrons are most likely to be found. Now there's different types of orbitals like the s orbital, which has a spherical shape, and each energy level has one s orbital. There's the p orbital, which has a dumbbell shape, and starting from the second energy level, each level has 3 p orbitals. Next, there is the d orbital, and this has a cloverleaf shape. And starting from the third energy level, there's going to be each level has 5 d orbitals. And finally, there's the f orbital, which starting from the fourth energy level Each level has 7 f orbitals. And orbitals can hold a maximum of 2 electrons for each orbital. So now we're going to talk about the principal quantum number. And this is represented by n. And it's the main energy level or shell of an electron in an atom. So there's n equals 1, 2, 3, and so on. And as n increases, the electron is farther away from the nucleus. And also, if n is higher, there is a higher energy. So if n equals 1, then the electron is in the first energy level and it's closest to the nucleus, and it also has the lowest energy. So now we're going to talk about energy sublevels. So in each principal energy level, there are energy sublevels. And sublevels divide each main energy level into specific types of orbitals like S, P, D, and F. And each sublevel has a certain amount of orbitals. And each orbital has 2 electrons. So for the S sublevel, there is 1 s orbital, and so there's 2 electrons. Since each orbital has 2 electrons. In the p sublevel, there's 3 p orbitals, and so there's 6 electrons. Because 3 times 2 electrons per orbital is 6. For the d sublevel, there's 5 d orbitals, and so there's 10 electrons total. Because 5 times 2 is 10 electrons. For the f sublevel, there's 7 f orbitals, and so there's 14 electrons in total. Because 7 times 2 is 14. So for n equals 1, the first energy level, we have a 1s since every energy level has an s orbital. For n equals 2, we have a 2s since all the energy levels have an s orbital. But starting from the second energy level, there are p orbitals. So we have a 2p. For n equals 3, we have a 3s, a 3p, but we also have a 3d because starting from the third energy level, we have d orbitals. And then for n equals 4, the fourth energy level, we have 4s, 4p, 4d, and we have 4f as well. And we can keep going. N equals 5, 5s, 5p, 5d, 5f. And we can keep going on. So now we're going to talk about the Aufbau principle. And the off-bell principle says that electrons fill the atomic orbitals in order of increasing energy. So what that means is that electrons occupy the lowest energy orbitals before filling higher energy orbitals. And so this follows the off-bell diagram. And so if there's 6 electrons, then the first 2 electrons will fill the 1s orbital, the next 2 fill the 2s orbital, and the last 2 start filling the 2p orbital. Next, we're going to talk about the Pauli exclusion principle. And the Pauli exclusion principle says that each orbital has a maximum of 2 electrons. And those 2 electrons have, when they occupy the same orbital, they have to have opposite spins. And finally, we're going to talk about Hund's rule, which says that electrons fill each orbital singly before they pair up. So now we're going to look at some examples of writing electron configurations. But first we need to write out off-Bell's diagram. So we're going to start with n equals 1, the first energy level. And we're going to have a 1s. And we're going to have 1 orbital. Because every energy level has 1s orbital. For n equals 2, we're going to have a 2s because each energy level has 1s orbital. And we're going to have a 2p because starting from the second energy level, each level has 3p orbitals. So we're going to draw 3 of these circles to represent orbitals. For n equals 3, we're going to have the 3s with 1s orbital, the 3p with 3p orbitals, but we're also going to have a 3d because starting from the third energy level, we have 5d orbitals. And then for n equals 4, we have 1s orbital, we have 3p orbitals, we have 5d orbitals, and we also have, starting at the fourth energy level, 7f orbitals. And then we can keep going up to n equals 7, but we're just going to stop here. So let's write out some electron configurations. So first, we're going to use nitrogen. And when we look on the periodic table, we can see that nitrogen has 7 protons, which means that it also has 7 electrons, since the number of protons equals the number of electrons in an atom. So we're going to write out it has 7 electrons. So when we write out the electron configuration, we're going to have a line to represent the orbital. And then we're going to look on the diagram and we're going to draw a diagonal right here. And we're going to draw some diagonals. And we can't go any further than that until we write more. But this right here is a 1s. So we're going to put a 1s. And each orbital has 2 electrons. So we're going to have a 2 right here for the electrons. And then we're going to have an up arrow and a down arrow to represent those 2 electrons. And it's an up arrow and a down arrow because the electrons have opposite spin. So after looking at this diagonal, we're going to look at this next diagonal right here. And we just have a 2s. So we're just going to have one orbital, one s orbital, and it's going to be 2s, again, 2 electrons. We're going to draw an up arrow and then a down arrow. So right now we have 4 electrons. We have 3 electrons left. So we're going to look at this diagonal next. And we have a 2p. 2p has 3 orbitals, and each of these lines represents an orbital. So we're going to have 3 lines just like this. We're going to put a 2p, but we only need 3 electrons. So we just put a 3 right here. And then we start by doing the up arrows first always, because of Hund's rule. And so, as you can see, 2 plus 2 plus 3 adds up to 7. And so this is our orbital diagram notation right here. And so we also want to know how to find the valence electrons. So the valence electrons are the electrons that are in the highest energy level or shell of an atom. So to find how many valence electrons there are, we're going to count the number of electrons in the highest principal energy level, which in this case would be 2. So for the energy level 2, we have this 2 and we have a 3. So 2 plus 3 equals 5 valence electrons. So for our next example, we're going to use the element magnesium. And when we look on the periodic table, we see that magnesium has 12 electrons. And so we're going to write out the electron configuration. So we start with that 1s2, up arrow, and then down arrow. 2s2, up arrow, down arrow. And then we look at this next diagonal, which says 2p6. So we're going to write 2p, and we're going to write 3 orbitals. And we have 4 orbitals already, plus 6 is 10. So we can fill up these completely. And then this next one, we keep going through this diagonal, is a 3s2. So we write 3s2, and there's just 2 electrons here. So this would be the orbital diagram notation for magnesium. So for our next example, we're going to use shorthand notation. So the 2 examples that we just did with the arrows are called orbital diagram notation. So this time we're going to do the same thing, except we're just not going to have the arrows or the lines. So for this example, we're going to do argon, Ar, which has 18 electrons. So we're going to start with 1s2, and then next diagonal 2s2, next diagonal 2p6, next subshell is 3s2, and then we look at this next diagonal. So we have a 3p, so we have 12 electrons, so we can do a 3p6. And so when we add up 2 plus 2 plus 6 plus 2 plus 6, we get 18. So this would be the shorthand electron configuration. And to find the valence electrons, we would look at the electrons in the highest principal energy level, which is the 3. So we have this 2 and this 6. So 2 plus 6 is 8 valence electrons. So for this next example, we're going to be using noble gas notation. But to do this, we need to label the periodic table with S, P, D, and F. So we're going to first start by crossing out this HE over here, and we're going to actually put it here. And this part right here is going to be the S. And then this part right here we're going to label D. This part right here we're going to label P, and this bottom part is going to be labeled F. The next thing we're going to do is we're going to number these rows with 1, 2, 3, 4, 5, 6, and 7. So let's look at an example of how to do this. So we're going to take Na as our example, and Na has 11 electrons, which is sodium. So this right here is Na. So what we're going to do is we're going to go all the way across, and then we're going to go up to get this right here, which is neon. So we're going to put neon in brackets. Then what we're going to do is we're going to subtract the amount of electrons in Na minus the amount in neon, which is 10, which just equals 1 electron. What we're going to do now is we're going to go down from neon back up to this row. We're going to go across, and we're going to see that it's right next to this 3. And it's also next to this S. So we're going to do 3s and just 1 electron, 1. And this is our noble gas notation for Na. And to find the number of valence electrons here, we just look at the number of electrons in this 3s subshell, which is the amount of electrons in the highest principal energy level, which is 3, which is just 1 valence electron. So for our last example of this video, we're going to look at Cl, or chlorine, and we can see that that has 17 electrons. So we're going to find chlorine on the periodic table, which is right here. We're going to go across up to this column of noble gases, and this is the noble gases, which is the last column in the periodic table. So we're going to go across and we're going to go up to find that it's neon again. That's going to be the noble gas. So we're going to write neon in brackets. And then we're going to go back down. We're going to go across. And we're going to see that there is a 3. So we're going to write 3. And it's also in right next to this S section. So we're going to write S2. Oh, and we need to find how many electrons we need to put. So 17 minus the 10 electrons of neon, which is 7 electrons. So we have the 3s2. So we have this 3s2. We're going to go to this next diagonal. And we have 3p right here. So we're going to write 3p, but we only need 5 because there's 7 electrons total. So when we see we have 5 plus 2 is 7, then we're good. So this is our noble gas configuration for chlorine. And to find the number of valence electrons, we count the number of electrons in the highest principal energy level, which is 3. So we have this 2 plus 5, which is 7 valence electrons. So that is it for today's video. I hope you guys enjoyed, and I'll see you in the next one.